Hello everyone, welcome back to Electronics 1. We've spent some time looking at the underlying details of how and why a bipolar junction transistor works. Now through that we came up with a set of equations that relate the various currents and voltages at the terminals together. We're going to now look at start with some very simple models to model a bipolar junction transistor in different modes of operation, and in a lecture or two we will introduce a more robust model that we'll use for the remainder of our discussions. Okay, so call this section BJT models, and we're going to look at saturation, which we haven't really addressed too much at this point, but we're going to look at some examples that of a device in saturation. Okay, so since the BJT has two junctions, it seems pretty reasonable that we could start with a simple model that's just based on two diodes. Okay, so using an NPN transistor as an example, where this is our collector, base, and emitter, we could equate this, again using a simple model, we could equate this to two diodes. So a diode from the base to collector, and another diode from the base to the emitter. Okay, so this is representing that base to collector junction. This is representing the base to emitter junction. Okay, and I suppose I should label this would be the base to collector voltage, and this would be the base to emitter voltage. Okay, so if we return to the different, to think about the different operating modes, we know that in cutoff, both diodes are reverse biased. And as such, we can assume that there's no current flowing between the collector and emitter, right? Because we know that at least for a reverse bias diode, that the current flow, the reverse current, is negligible, and only due to that drift current, which is very small. So we'll assume that in cutoff, both diodes reverse bias, no current. Okay, whereas in saturation, you'll recall that this mode of operation occurs when both diodes are forward biased. And in that mode, if we think about a diode in the most simplistic sense, like a closed switch when it's forward bias, we can imagine that we can treat the collector and emitter, I should label the collector emitter base. We can, if both of those diodes are forward biased and acting like a closed switch, we can treat the collector and emitter as though they're connected together. Okay, so this is in saturation. Okay, and finally, in the mode that we said we'll spend the most time on, is forward active. So in forward active mode, the base to emitter diode in our model is forward biased, while the base to collector diode is reverse biased. Okay. So in this mode, or in this configuration, this is the mode of operation that we went through the derivations of the equations and looked at, and we found that the collector and emitter currents are nearly equal. And we also found that those currents are a function of the base to emitter voltage. Right, because we said that the collector current is equal to our saturation current times e to the VBE over VT. Okay, and of course we said that the emitter current is nearly equal to the collector current. It's beta plus 1 divided by beta times the collector current. So again, just slightly higher. Okay, so with these things in mind, let's and using the equations that were presented in the last lecture, let's go through a simple example and see if we can solve for the kind of the operating point, the currents and voltages of a transistor. Okay, so let's call this example 1. Okay, and in this example we'll have our NPN transistor. We're going to connect the base directly to ground. I'm going to take the collector and connect it up to a 10 volt power supply. I'm going to call this VCC, so this is plus 10 volts. And we're going to collect it through a resistor. We're going to call this the collector resistor because it's connected to the collector. And this resistor is 5 kiloohms. And we're going to put in the resistor on the emitter. We'll call this RE. And that resistor will be 10 kiloohms. And it's going to go to a minus 10 volt source. And this we'll call VEE. Okay, these namings of the power supplies may look familiar. This is some of the same convention you'll see on integrated circuits, VCC and VEE. Okay, let me label a couple more points. Let's label this point right at the collector as in terms of the voltage. We want to know what the voltage is at that point, so that's the voltage at the collector, or VC. Of course, it's at the collector with respect to ground. and the voltage at the emitter with respect to ground I'm going to call VE. Okay. Now list a few parameters that are given about the transistor. So let's assume the transistor has a common emitter current gain, or often just called the beta of the transistor. Let's assume that it's 50. That's kind of a ballpark typical value. And let's assume that we know that the base to emitter has a voltage of 0.7 volts across it. Okay, and actually let's go a little bit different route. Let's assume we know that the emitter voltage is minus 0.7 volts. Okay, and you can appreciate that, well, if this is the emitter voltage here is minus 0.7 volts, and the base voltage that's over here is tied to ground or 0 volts, then we can conclude that the voltage at the base with respect to the emitter, which is voltage at base minus the voltage at the emitter, is 0 volts minus 0.7 volts, or we could say that the base to emitter voltage is 0.7 volts. This should not be a surprising value if our assumption is that this device is operating in forward active mode. That means that the base to emitter junction is forward bias, and 0.7 volts is a pretty typical forward bias voltage of a PN junction. Okay, so what is it we're trying to find? So I want to find the following. Find what the emitter current is, to find what the base current is, to find the collector current, and let's find out what the voltage at the collector is. Okay, now I'm just going to label here this, the emitter current, of course, is the current coming out of the emitter. The base current is, of course, the current into the base. The collector current is, of course, the current into the collector. Okay, let's look at how we tackle this. And after all that background, looking into how transistors work, you might be a bit intimidated by BJT transistors, but they really aren't. They really just become a fairly simple circuit problem, and we just use those relationships between our currents to solve for the operating point. Okay, so let's call the voltage across this resistor RE, let's call the voltage across that VRE. Okay, so the voltage across the emitter resistor, let's call that VRE. Okay, and that would be this voltage drop that's caused by IE. So VRE is this voltage here. Okay, while VRE is going to be the voltage at the top of the resistor, which is VE, minus the voltage at the bottom of the resistor, which is minus 10 volts. Okay, so we know that the voltage VE is minus 0.7 volts. We know that this is going to be 10 volts, so the voltage across RE is equal to 9.3 volts. Okay, that's the voltage drop across this resistor. If we know the resistance and we know the voltage drop, simple Ohm's law calculation will allow us to calculate the current through that resistor. So 9.3 volts across a 10 kilo ohm resistor, which means that we have 0.93 milliamps of current flowing through that resistor. Okay. You will recall that beta was given, the common emitter current gain was given as 50. From that we can solve for alpha. We could use beta directly, but let's solve for alpha as well. Alpha is beta over beta plus 1, so 50 over 51, and this gives an alpha value of 0.98. Okay, I know that my relationship between collector current and emitter current is alpha times IE, so 0.98 times a emitter current of 0.93 milliamps gives me a collector current of 0.91 milliamps, and we said that the collector current should be slightly lower than the emitter current. Okay, we could have done this with beta directly, of course, as well. We could have said that the collector current is equal to beta over beta plus 1 times IE as well. Okay, so we have the emitter current, we have the collector current. Now that we have the collector current, so that collector current in this diagram is the current that's through this resistor, RC, right? This is the same current here. That resistor is in series with the collector. So knowing that, we can calculate the voltage at the bottom of that resistor. So the voltage at the collector is going to be the voltage at the top of the resistor, which was that voltage VCC, which was plus 10 volts, minus the voltage drop that occurs through that resistor. So minus the collector current times the collector resistance. Okay, so and maybe let me put in that this value was the VCC value. Okay, so 10 volts minus a collector current of 0. And just be careful of your units here. I'm going to write this in amps just to make sure there's no confusion, times my collector resistance of 5,000 ohms, and this gives me a voltage at the collector of 5.45 volts. Okay, I guess what else were we looking for? I've got the emitter current, the collector current, the collector voltage, the base current. Okay, we will recall that our derivation showed that we can calculate the base current as the collector current divided by beta. Okay, so the collector current was 0.91 milliamps. So the base current is 50 times less than that, or 18 microamps. Okay, so there's our final value. Okay, so we've fully solved for that circuit. Let's just do a check here. One thing that I want to make absolutely clear is when we're using these equations that we derived over the past couple classes, so like equations like that and equations like this that relate the base and collector and emitter current, our assumption is that, and I guess this assumption is that the device is operating in forward active mode. Those equations are only valid in forward active mode. So when we do an analysis using those equations, we are making an assumption that the device is in forward active mode. So we should always check to make sure that using those equations that we can confirm that the device is in fact in forward active mode. Okay, so we need to check and validate that it was appropriate to use these equations. Okay, so just to say that that analysis that we just completed was done assuming that we were in forward active mode. Okay, so let's return to, let's just show just the bipolar junction transistor itself from the circuit. Okay, and if I'm representing each of these junctions using just a diode model, okay, so this is essentially what each of these junctions is being represented as. This is representing the base to collector junction, which I'm hoping is reverse biased. This is representing my base to emitter junction, which I'm hoping is forward biased in order to have the device operating in forward active mode. Okay, so we see that the base is grounded. That's clear. We knew that the voltage at the emitter was minus 0.7 volts. That was given. And up here we calculated that the voltage across the collector with this assumption of forward active mode was 5.45 volts. Okay, so let's confirm that the device is in forward active mode. So let's look at the base to emitter junction. Okay, well, the base is at 0 volts, the emitter is at minus 0.7 volts, so the base to emitter voltage, and I actually did this calculation up above, is 0.7 volts. Great, right? This is great. This is forward active, maybe. Okay. Or, well, I guess we don't know forward active yet, but we at least know that this junction is forward biased. Okay, but we have to know that it was in forward active mode, we have to also look at the base to collector junction to confirm that it was reverse biased. Okay, again, we know that the base is at 0 volts, and we calculated the collector using the assumption of forward bias was at 5.45 volts. So base to collector is, of course, the voltage at the base minus the voltage at the collector, and that is going to give us a voltage of minus 5.45 volts from base to collector. Now we'll remember that this is an NPN transistor, so this base is P-type, this collector is N-type. Up here the base is P-type, the emitter is N-type. So if the base is 5.45 volts lower than the collector, then this device is reverse biased. Okay, as indicated here by the negative sign. Okay, so we are reverse bias. So the mode is confirmed then to be forward active. Okay, let's look at another example. Let's call this example 2. Okay, so let's do a slightly modified version of our circuit. I'm going to connect the emitter resistor to ground this time. I'm going to assume we have 6 volts applied to the base, and we have 10 volts applied to the top of the collector resistor. Okay, so this is VCC is 10 volts. We're applying 6 volts to the base. This collector resistor is 4.7 kiloohms. The emitter resistor is 3.3 kiloohms. Okay. What are we given for this case? Let's assume we're told that alpha is equal to 1 and that VBE is equal to 0.7 volts. And we're asked to, find all voltages and currents. Okay, let's stop here for a second and think about what is the significance of alpha being equal to 1. Well, alpha equal to 1 means that our collector and emitter currents are identical. So this is representing an ideal BJT. So maybe not practical, but so be it. So this is assuming the collector current and emitter current are equal, and also that my base current is 0. Okay, so let's take a similar approach, and let's start out by assuming that we're in forward active mode and that we can use our forward active mode equations. Okay, so let's start by finding the voltage VE. Okay, so the voltage VE is going to be equal to the voltage at B minus VBE, right? So if we know the voltage at B here is equal to 6 volts, we know that this drop was given as 0.7 volts, then we can find the voltage at E. Okay, so 6 volts minus 0.7 volts gives us an emitter voltage of 5.3 volts. Okay, we know now the voltage across RE here, this voltage from here to here, let's call that VRE. So VRE is actually just equal to the emitter voltage because the bottom of the resistor is connected to ground. Okay, so this is equal to 5.3 volts, and we can therefore calculate the emitter current as this voltage VE divided by the emitter resistance. Okay, so 5.3 volts divided by 3,300 ohms, or 3.3 kiloohms, gives us a current of 1.6 milliamps. Okay, now we said up above that alpha was equal to 1. Alpha equal to 1, we said, means that the collector current is equal to the emitter current. Okay, so the collector current, we can conclude, is also equal to 1.6 milliamps. Okay, knowing the collector current, so knowing that this current is 1.6 milliamps, well, we can calculate the voltage drop across the collector resistor as the voltage at the top of the collector resistor minus the voltage at the bottom of the collector resistor. Let's just calculate the voltage at the bottom of the collector resistor, I guess, first, and we already have the current, I guess, so we calculate the voltage at the bottom of the collector resistor as the voltage at the top minus the drop across the collector resistor. Okay, the voltage at the top was 10 volts, and 10 volts minus the 1.6 milliamps, oops, times the 4.7 kilo ohm resistance gives us a voltage at the collector of 2.48 volts. Okay, so I've got my voltage at the base was given. I've got my emitter voltage here. I've got my collector voltage. I've got my emitter current, and I've got my collector current, and in fact I have my base current, although I didn't state it, but again, this my base current would be equal to 0, because we'll remember that base current is the difference between emitter current and collector current, and in this case that difference is 0, because we're assuming an ideal BJT, which is again not realistic, but for the purpose of this equation, or for this problem, just to prove a point here and just to simplify the problem. Okay, so let's we were told that VBE was 0.7 volts. Okay, so right away that was given, and we know that that base to emitter junction was forward biased. But what about the base to collector? Okay, we're told that we're given that the base was 6 volts, and we're just solved here that the collector is let me write this out here, I guess. The voltage at the base minus the voltage at the collector is the 6 volts minus 2.48 volts. This gives a value of 3.52 volts, positive 3.52 volts. So this is an important discovery here, in that this is also forward biased. Therefore, the combination of these two both being in forward bias means that the device is not in fact in forward active mode, it's in saturation. Okay, so our assumption, right? What assumption? This assumption that it was in forward active mode, that allowed us to use all these forward active mode equations, that assumption was wrong. Okay, so what's that mean? Well, it means we have to take a different approach to solve for the operating point of our diode, or of our BJT. So let's use initially let's use a simple method of coming up with a solution for a device in saturation. So let's use our ideal diode model. Okay, so again, what we are doing is we are modeling our, let me try to fix this up here a little bit. We're trying to model this BJT as two diodes, two PN junctions. Right? Our base to collector junction and our base to emitter junction. Except in this particular example, example 2 that we just looked at, we said that both diodes are forward biased or on when we think about them in an ideal diode model. So we remember that, that the ideal diode model says that we model a diode basically just as an open or closed switch. So if we model both these diodes as a closed switch, our BJT simply becomes a simple model that has the base, collector, and emitter all connected together. Okay, so this is our simplified model using an ideal diode model, and here we'll note that VBE has to be 0, right? Because base and the emitter are connected together. Okay, so let's substitute this simplified model using the ideal diode model into our circuit. Okay, so our circuit from earlier, so this circuit that we started with up here, this circuit becomes just this. When we assume the devices are in saturation and use our ideal diode model. Okay, so again, you'll also note that the voltage at the collector equals the voltage at the emitter equals the voltage at the base, which in this circuit was 6 volts. So now if we just use simple circuit analysis techniques to solve for this circuit, we can say, well, the collector current here, this current here, we can solve for the emitter current, the current here, we can solve for, and of course the base current being the difference between those two. So let's solve for those. So the collector current is simply going to be equal to the VCC minus the voltage at the collector, which is the voltage at the base, divided by the collector resistance. So this is 10 volts minus 6 volts divided by 4.7 kilo ohms. And this gives us a collector current of 0.85 milliamps. The emitter current, again, we can't use those forward active mode equations because those equations are for forward active mode. So here we're just going to use simple circuit analysis techniques. So the voltage or the current through the emitter resistor, or the current from the emitter, is the current at the emitter divided by the emitter resistance, because that's the voltage across that resistor. This is therefore 6 volts divided by 3.3 kilo ohms, or 1.82 milliamps. And of course we calculate the base current is the difference between the emitter current and the collector current, and is 0.97 milliamps. We notice it's substantially higher than in our first example. Let's, knowing these values, we could calculate what we call an effective beta. So the effective beta value, knowing that beta is the ratio of collector current to base current, is 0.87. Okay, so much lower than that the actual beta value of the transistor. This is an effective beta value of the circuit, or a sometimes referred to as a forced beta value. Okay, and again, we'll note that this is very low. Okay, so that's solving for a device in saturation mode, making some pretty bold assumptions, and using that ideal diode model. We're going to come back to this next lecture and solve for the operation in saturation using a little bit more appropriate model for our junctions, for each of our junctions, and therefore for our BJT.